Okay, so we have looked at matrix multiplication faster than the naive n cubed algorithm using divide and conquer. We looked at integer multiplication, and today we are going to look at polynomial multiplication using divide and conquer. So, let us say you have two polynomials on one variable, and we want to compute the product polynomial. Okay. So, you know how to multiply this, right? You have learned again in school. So, it is A0 B0 plus for the x term it will be A0 B1 plus B0 A1 for x square and so on and so forth. So, it will be basically you have AI, right. So, you have there are some x power k terms where k would range from 0 to 2n minus 2, and what is the coefficient of x power k? You take x power I from here and x power k minus I from here and multiply, right. So, x power I term is ai and x power k minus I term is bk for various values of I. Right. So, when you set I equal to 0, what this is bk, so that will give you an x power k, and then you have a1 bk minus 1 and so on and so forth. So, this is how you will get your the product polynomial of degree 2n, right. So, how much time would this take? How many multiplications, let us say, n square, right? Does everyone see this? It's basically 1 plus 2 plus 3 plus kind of thing. The constant term will be 1, x term will be, there will be 2 terms, x square would be 3 terms and so on. So, it will be an n square algorithm, and we are going to use divide and conquer to improve the running time to get to n log n. Okay, that is the goal. Okay, so the way we are going to do it is we actually are going to change the representation of the polynomial. So, this is called coefficient representation. Now, we will use the observation that you can get the coefficient of, or you can determine uniquely a polynomial of degree n by knowing its value on n distinct points, right. So, if I know Ax is uniquely determined by Axi for n distinct points xi, where I ranges from, let us say, 0 to n minus 1. So, if you tell me the value of the polynomial on n distinct points, it's the same as saying 2 points determine a line, right. So, this is same as saying, so how would I find the A0 if I know Axi? How can I find the coefficients? So, suppose I tell you Ax0, Ax1, Axn minus 1 for some n values x0 to xn minus 1. How do I get the coefficients? So, you have n equations, you solve them, and n equations, n unknowns, and you will be able to get those coefficients, right. assuming those equations are linearly independent, or in other words, right. So AXI, what is AXI? It's A0 plus A1 xi plus A2 xi square plus, that's what it is. So if I know, if I write this for AXI I equal to 0 to n minus 1. So if I know these values, so I have n equations on n unknowns. The unknowns are A0, A1, A2, n minus 1. Solve those equations and I get the coefficients, right. So this is a, that's a proof of this statement. What is the proof? Well, that these equations are sufficiently independent that you can actually solve them. Well, how do I prove that? The way to write this is, so I have this 1x0 x0 square 1 x1 square x1 power n minus 1 1 xn minus 1 xin minus 1 square xn minus 1 power n minus 1 into a0 a1 an minus 1 is exactly ax0 ax1 axn minus 1, right, because ax0 is essentially this first term, which is a0 plus a1 x naught plus blah blah blah, you get this. Ax1, you take the second row and do a multiplication, you get this. So what these values, suppose I tell you these values, I tell you the x0, x1, x2, xn minus 1, so I know this matrix, I know these values, I want to find these coefficients. How do I find these coefficients? I get, let's call this matrix as some V, then A0, A1, an minus 1 is nothing but V inverse into your Ax naught okay. So V times this column vector is this column vector. So if you want to know this column vector is V inverse this thing, and why does, so all I need to argue is that V inverse exists, right. In other words, a determinant of this matrix is non-zero, and the determinant of the matrix is a very special matrix. It turns out this is basically product xi minus xj, I less than j or something like this. Since all the xi's are distinct, all these terms are non-zero, so this product is non-zero. So the determinant is non-zero, so the determinant inverse exists. So this is the way you can compute the AIs, right. I am not discussed the computational aspect yet, that we'll come to that, but for now I am just trying to argue this. So all I am saying is another way to represent your polynomial is by ax0, ax1, axn minus 1. So if you give me the polynomial's value on n different points, n distinct points, that's another way to know the polynomial. Okay. But why do I care about that representation? Because in that representation, multiplying two polynomials is pretty easy, right? Because let's extend our domain to polynomials of degree 2n, because when I do multiplications, I am going to get polynomials of degree 2n. So for me, the 2n is the n. Okay. So if I have the value of the polynomial on n different points, on n fixed points, so I decide some n fixed points or 2n fixed points I decide, and the way I am going to represent every polynomial in this world is by knowing the value of the polynomial on these points. Okay. So that is the point value representation. So I have x0, y0, x1, y1. So to get an nth degree polynomial, its value at n points are enough, but let's say I store some 2n points because when I multiply I get 2n degree polynomial. So now if I have two polynomials and b stored in this way, now can I compute AB? How do I compute AB? So I have a polynomial A stored by evaluating the polynomial. Let's not worry about how much time it takes, we'll come to that. But suppose I have this representation of the polynomial, which is simply that polynomial's value on these n different points, and I have another polynomial of degree n, and I've stored its value on n different points. Now I want to compute the product AB polynomial. What do I do? In this representation, I need to know its value on these n different points. How do I do? Yes? Sorry? Yeah, multiply pointwise. Is that a difficult question? I want to know what is AB of x naught. AB of x naught is basically A of x naught times B of x naught. Right? AB is a product polynomial which is looking like this. I want to evaluate it at x naught, but it is simply the polynomial A's x naught value times B's x naught value, which I have stored here. So I just take the pointwise, multiply them. Right? So in this, why do I care about this representation? Because in this representation, multiplication can be done in linear time. Because all I have to do is to take the pointwise values and multiply them. Right? Okay, but it's not the end of the story, because often polynomials are given this way, right? And you really want to compute this product here, not in this representation. One way I could do it is start from here, get to this representation, multiply in linear time, and then get back to this representation. Okay, so let's see now how much time does it take to evaluate A on some n different points, n or 2n different points. Right? How much time does it take to compute this AXI? Suppose I am given in coefficient form. I want to just plug in value x naught, evaluate it, compute it. Plug in value x1, evaluate it, compute it. How much time will it take? N square, right? Because I can compute the x naught square, x naught power n minus 1 in linear time, and then I multiply a naught, a1, add them all. So the whole thing for each evaluation is going to take me linear time. So overall, n evaluations, n square time. Okay. Question is, can I evaluate it faster? Right? I want to evaluate in n log n time. And what is the leeway I have? The leeway I have is that these points are my choice. Any n distinct points can determine my coefficient representation. So can I come up with some interesting set of n points where evaluation would be faster? Okay. So that's the question we want to address. And similarly, also I want to do the multiplication and come back here also, the same problem. I want to come back here faster in n log n time. Okay, so that's the goal. So first goal, let's get to that. I have a polynomial in this coefficient representation. I want to come up with n different points where I can evaluate using divide and conquer in n log n time. Okay, because these n points, all I know is they have to be distinct. Other than that, they can be completely arbitrary in my field, whatever I am working on. Okay. So, evaluating A on n distinct points in n log n time, that is our goal. Okay. And n log n, you know what, immediately tells you what sort of recurrence we are aiming for, right? We've seen it in merge sort, various other problems. So, we want to divide it into problem 2 halves and then put them together in linear time. Okay. Right. So, this is our sub goal now, because basically we want to move from this coefficient representation to point value representation in n log n time. Then we use this multiply in linear time, and then we will worry about coming back here. Okay. So, again we are going to assume n is a power of 2. Otherwise, you can add some 0 coefficients and make your polynomial extended to n x power of 2. So let's write my polynomial like this. Let's take the even terms a0 plus a2 x square plus a power 4 x power 4 blah blah blah. So, a n minus 2 x power n minus 2. So, let us call this a e of x. An odd term, I am going to write this as a1 plus a3x square plus a5 x power 4 then what is a of x? aex plus x times a o x, right, because it is actually a1x, so I have to multiply by x to get that. All right. Right, but actually why should I write like x square? I am going to change it to x square, and similarly this is x square and n minus 2 by 2. Then what is okay? So, I have again rewritten. So, instead of x I have to plug in x square here. So, instead of x I have to plug in x square to get x power 4. So, this is my a0, a of x. Okay, I have taken I've gotten a polynomial of half the degree with only the odd coefficients and another one with even coefficients, and turns out I have written ax something like this. Okay. Now, I have to evaluate ax at some n different points. Okay, that is my goal, a at n different points. Now, suppose I choose my points, let us say, so I choose x0, x1, x n minus 2 by 2, or which is basically n by 2 minus 1, and then minus x0, minus x1, minus x n by 2 minus 1. So, you want me to evaluate a at n different points. My n points are as follows, that half of them are plus minus. Now, let us come back and evaluate a at these n different points. Notice that when I want to evaluate at minus x naught, a of minus x naught, by plugging in here, is simply ae of x naught square minus x naught into a naught of x naught square, right, because I just plugged in. So, this is the same with all the minus terms. So, do you see some savings in work now? Because what do I have to evaluate? I have to evaluate AE on only the square of these guys. There are only n by 2 of terms. Okay. So, I am evaluating AE is a polynomial of degree n by 2 minus 1, and I am evaluating at some n by 2 points. Same with A naught. That is all I need to do. That is the work I need to do. After that, to compute A at these values, I can just reuse some of the work which I have already done here. Is that clear? Do we have a divide and conquer algorithm? Do we have an n log n algorithm? Question? So, my algorithm now is you want to evaluate A at these endpoints. Evaluate AE at the square of these points. Okay, that is only n by 2 points, and that is a polynomial of degree n by 2 minus 1. So, evaluate it. So, I am evaluating an n by 2 polynomial with on n by 2 points. Similarly, evaluate A0 at the same square, same points, n by 2 points, because this square are the same, right? And then I need to put them together. Whenever I want to evaluate A at these points, take the square, the difference is here. I do a plus. Whenever I want to evaluate these points, I take the square values and put a minus. So, that is a linear time work. For each one, I am just plugging in value from here, multiplying by x and adding it. Okay. So, I claim my T of n is 2 T of n by 2 plus order n. So, I am not done yet, by the way, I am just tricking you. I want to see who gets the issue. But so, what I am saying is, to evaluate, here is my entire algorithm. A at x0 x n by 2 minus 1 minus x naught minus x1 minus x n by 2 minus 1. Evaluate A naught. Yeah? Sorry? No, I didn't get it.
Video was stuck.
Oh, video was stuck. Okay. Video is the problem. Okay. X0 square, x1 square, xn by 2 minus 1 square, and AE at the same points, and use the formula that A of x0 to x n by 2 minus 1 would be, whatever, AE of x0 square plus x naught into AO of x0 square, which you already computed. And for the other guys, it's basically AE of x naught square minus x naught into A naught x naught square. So, this whole thing is a linear. So, my recursive call are these two recursive calls of size n by 2, and then this is a linear time thing to put things together. Are we done? There is one problem. Let's go to the recursion step. Is it the same as what we started off with? That's not a problem. That's just some n multiplications. So what? It's another polynomial of degree n by 2. Sorry? So let's look at where are we evaluating A at? What we are evaluating A at some endpoints. What is the property of those endpoints? That half of them are same, plus minus, right? That's the top level version of the problem, right? But don't you also want that at the recursion step as well for us to apply the same algorithm, right? So what does that mean? Because I am evaluating A naught at some arbitrary n by 2 points. I don't know how to do that. All I am saying is, if you give me n points where only half of them are same, the other is the minus of these guys, then this recursion works. But I need to ensure that these points also have the property that, one half is plus and the other half is exactly minus of those guys, then only I can apply the recursion. I mean, the way my ability to break it up and use this idea that, oh, these are plus, minus, the same thing. Okay, this is very, very important. When you look at recursive algorithms, just make sure at the recursion step, it's like induction, right? You need to make sure the induction hypothesis is exactly satisfied in your induction step. So, when I am evaluating A naught and E naught at these n by 2 points, I don't know how to recursively evaluate at arbitrary n by 2 points. This method says that if these points are plus and minus of some n by 4 pairs, then I will be able to do it. So now let's choose our points, even exercise our choice on the points more. It's not just about n by 2 points which are plus and minus. I will also make sure that these guys are plus and minus of this, not at this step, at every step. Let's see what this takes us to, right? So, and here is another problem. You're talking about squares. How can squares be negative of somebody? Can squares be negative? When you get to complex numbers. So let's get to complex numbers and evaluate them, right? Squares, can they be negative? Yes, I square is minus 1. It is negative, right? So it's possible. So let's draw a picture of what we want. So at the bottom, I have some plus 1 and minus 1 I want. And then I want again some plus 1, minus 1 here, this roots. So I want the squares to be plus 1, minus 1. So the square, so that means this has to be like I and minus I. This, right, square root of minus 1. So this will be 1 minus 1, and this will be an I and a minus I, and this will be square root of I, complex square roots of I, plus and positive, negative. Overall, what does this lead to? It takes us to the nth roots of unity. Okay, so let us choose x0, x1, xn minus 1 to be the nth roots of unity, the complex nth roots of unity. Okay. So hopefully you've all seen, most of you are math students, you've seen complex nth roots of unity. Typically it's e power 2 pi I by n, right? This is the primitive root, complex nth roots of unity, and so the roots are 1 omega n, n square. So this is now going to be my set of n points on which I am going to evaluate the polynomial. And now let's get to the theory to argue that it has the nice properties I need on the recursive steps. Okay. So what is it I need on the recursive step? They are all this plus minus 1 thing, right? First of all, omega n power n by 2 plus I. Let's write down some properties. Okay, so let's use this formula that it is cos theta plus I sin theta. So this is my omega n. What is n by 2 plus I? Well, what is omega n power n by 2? If I just plug it in here, the n by 2 will go away. It will be e power pi I, which is cos pi plus I sin pi, which is minus 1. So this whole thing would be minus 1. So this will be omega. Okay. So which is a nice thing, because what this says is that up to n by 2 terms are distinct, and after that it's a minus of the same terms before. Right, omega n by 2 plus I is the same as minus omega n square, I, omega n power I. So it has this plus minus property I want, not at this step, at every step, because, okay, so property 1. What are the other properties? 1 omega n square omega n power 4. Basically, if you take the square of these, they are the same thing, which is the first half and the second half are repeating because of this property. Right? These are plus. So basically, so 1 omega n square, omega n power 4, omega n by 2 power whatever n, or n by 2th roots of unity. So when I want to evaluate A0 at these squares, these are exactly n by 2th roots of unity, which I am evaluating on an n by 2 degree polynomial, and similarly same with AU. So it has the recursive substructure which I want, right, because I am evaluating at nth roots of unity. So when I break it up into AE and AO and look at half degree polynomial, it turns out I am evaluating at the square of these things anyway, and the squares are the n by 2th roots of unity. So I have the recursive structure. Now it is 2Tn by 2 plus order n, because it is exactly, because I am evaluating my nth degree polynomial at n complex nth roots of unity. So when I break it up, it becomes, because of these nice properties, it's because it has the exact recursive substructure. Okay, so now we know, instead of choosing some arbitrary points, if I choose my nth roots of unity as the points, then I can apply my divide and conquer, and this way of breaking it up gives you a nice n log n algorithm to evaluate my polynomial on these points. Okay, good. So that's the one step of the multiplication of polynomials, because they given a coefficient representation, apply this and evaluate the polynomial on these n. And if you really want 2n, then it just take the 2nth roots of unity and evaluate them at these points, and then do it for the b polynomial, and then do a pointwise multiplication. Now I want to answer back in coefficient representation. Okay, so that takes us to this problem of interpolation, right? This is evaluation. The other is that suppose I give you, this is the inversion of the Vanderman's matrix. Okay, again, it's not an arbitrary Vanderman's matrix because that inversion will still take n square time, but we want to use the fact that the matrix is of this special form. Okay, so this is done. The second point I want to talk about is interpolation, which is given some ax0, axi, I equal to 0 to n minus 1, where not arbitrary xi is my omega n, the ith power of the primitive nth root of unity. Compute a0, a1, an minus 1. I want to get the coefficient, right? So given a polynomial in coefficient form, we evaluate it on these points, get the point value representation, do a pointwise multiplication, and get the product polynomial in the point value representation, and then we are going to apply this to get back the coefficient of the product polynomial. Okay. So let's again write it in that matrix form. What did we do? We had this matrix. So this is 1, 1, 1, 1, 1. So when I evaluate the polynomial at 1, 1, 1, it's a0 plus a1 plus up to an minus 1. So that's what it will get, a1. And what is this matrix next here? It's 1 omega n square, no, yes, omega n power n minus 1, right? Because a0 plus a1 omega 1 plus a2 omega 1 square. So this is exactly a of omega n. And finally, I will have 1 omega n power n minus 1, omega n power 2 into n minus 1. Again, this Vanderman's matrix, but this is a special matrix, not an arbitrary exercise, but these special values, right? So now what do I want? So in fact, there is a name for it. This is called discrete Fourier transform. So I would say these is the discrete Fourier transform of the vector a0, a1, an minus 1. Basically, given some vector, you apply this matrix, and what you get is the transform, right? This vector is transformed into this vector. Okay, so this has a lot of applications in signal processing and so on. You might have seen in your electrical engineering courses. So now what I want is the inverse of this matrix, right? Because you are given these values, I want to get the coefficient AIs. So this AIs is basically V inverse times this. So if I have a nice way of computing V inverse matrix, I am in good shape, right? That's the interpolation problem. So let's write down more properties of this nth roots of unity. What do you know about 1 plus omega n plus omega n square plus so when n is greater than 1. Okay, right. This is a geometric series. So sum them up, what do you get? Huh? 0. Omega n power n minus 1 by omega n minus 1. So this is 0. Okay, this is useful to know. We'll, in fact, yeah, okay. So this will come handy. So all I'm going to do is to tell you, okay, what is Vij? What is the ijth entry of this matrix? Okay, so let's say this is first row, or if you like, let's write this as 0th row and n minus 1th row, 0th column and minus 1th column. So what is Vij in this matrix? So ith row is talking about evaluating the polynomial on omega n power I. So jth column would be, so omega n I power ij, right? Here is my claim about V inverse. Minus Ji, and what it is, let's see. Okay, what is omega n power minus something means? Basically n minus that, because omega n power n is 1. So minus the inverse is basically, you can think of it. So in fact, if you think of the powers, they form a group in the integers modulo n. So additive group. Okay, so basically, so this is same as omega n power n minus ji. Okay, so this is my claim. All I'm claiming you, I'll just tell you the ijth entry of the inverse of this matrix. We'll verify this first, and then we will see how to compute the inverse. Okay, computing the inverse, now you should get an idea that it turns out that more or less the same kind of a problem. Instead of omega n, we are going to do it on the inverse thing. There is a 1 by n. Okay, I'm going to write this. Yes. Okay, so how do I prove? I'll prove that this product is identity, right? So let's take some let's look at the ijth entry of this. This is summation k going from 0 to n minus 1 Vik into V inverse Kj. Well, what is Vik? This is summation k equal to 0 to n minus 1 omega n Ik into omega n minus Jk. Okay. Okay, I'm going to erase this because you know what I'm trying to compute. I'm trying to compute V inverse, where Vij is this matrix, right? So that's this matrix. So V inverse ijth entry is nothing but summation k equal to 0 to n minus 1 omega n k times I minus j. Oh, there is a 1 by n also, right? Yeah. Because there is a, I wrote the 1 by n. Okay. What is this when I is equal to j? Yeah. When I is equal to j, it's because this term is 1, because when I is equal to j, I minus j is 0, anything power 0 is 1, so each term is 1, there are n terms, so it is n by n, so this is equal to 1 if I equal to j, and if I is not equal to j, it is sort of this sum, right, because take the I minus, yeah, so you can take the omega n power I minus j, which I am summing from 0 to n minus 1. So the whole thing would be like this whole power I minus j power n minus 1, power n will kill you into 1 minus 1. So this is 0 if I is not equal to j. So the product is an identity matrix. So that is correctly the inverse matrix. So now what do I want? I know that my A0 to a n minus 1 which I want is the coefficient is nothing but V inverse into AX0 or A of 1 A of omega n. So if I can compute V inverse and then I can multiply by this and I get my coefficients. Now if you look at it, V inverse is also like a discrete Fourier transform because it's just, you know, instead of evaluating my A0 A1 polynomial at the 1 omega n power n minus 1 points, I have to evaluate these coefficients, these polynomial. Think of it as, you know, A1 plus A omega n x plus that this polynomial. So it's basically I'm applying the same kind of a transform on this vector. The only difference is instead of, you know, ij I have ji, which is sort of a, you know, transpose of the matrix, and I am applying it for omega n power minus 1. That is also a primitive nth root of unity. So essentially the same discrete Fourier transform idea works. Okay, I'm going to leave that as an exercise to fill the details, but there's nothing magic going on here. It's essentially the same. Now, what did we do earlier? We have this matrix which looked like this 1 omega n, which applied on this coefficients and we got this, right? Now, apply not that matrix but something similar looking matrix on these points. And how is it similar looking? Well, the only difference is one is there is an n here and there is a minus here. Otherwise, it's the same. And there is a transpose part of it because the ith term here was ij, here it's ji. Okay, so V inverse is also a discrete Fourier transform. Matrix, so, you know, A1 this can be computed in Okay, so the way I've stated it, there are a couple of comments. One is I've stated it recursively, but you can actually do it iteratively, just like many of the recursion algorithms like merge sort, you can actually go bottom up and gradually get to the top. So in fact, many of these operations can be even parallelized. You can build a nice parallel circuit to evaluate fast Fourier transform of this vector. Another important point is that we are doing complex multiplications, right? Because when I say n log n time, we are multiplying by omega n minus omega n. So it's like complex numbers. When you go and represent them in computer, you have some precision issues. All that is there, but it turns out you don't have to take your entire domain of complex numbers to do this. You can take a large ring of integers modulo some large m, okay, and you can argue that in that ring of integers you have complex nth roots of unity sitting in there in your additive group and work with that. So then it's actually integers, okay, it's not really complex numbers, it's complex roots of unity in a large ring of integers, okay. So you are math students, you should be able to at least pick this up and check what I mean by that. But it's an important remark that when I say n log n time, I'm actually here referring to multiplying by complex numbers, but you don't need to. You can actually work with a ring of integers modulo some large m and things work out fine. Okay, it's all integers. Maybe it's somewhat large integers, but it still is fine. Okay, so here, so that's all about fast Fourier transform. Nice way to multiply. In fact, this is useful for integer multiplication too. Remember, because if you have n bit numbers, so if I have a0, a1, an minus 1, which is an n bit number, what is its value? Okay, so maybe I will start a0 here and an minus 2 and an minus 1. What is its value? Its value is an minus 1 into 2 power n minus 1 plus an minus 2 into 2 power n minus 2 plus a1 into 2 plus a0, right? This is its value, right? And so if I have to multiply two n bit numbers, it's like multiplying two n degree or n minus 1 degree polynomials and then evaluate them at this number 2, right? So this whole FFT also gives you a fast way to multiply two integers, okay. Not quite in n log n time because it requires a careful definition of what it means by time, because the point I mentioned about you're dealing with complex numbers and stuff, right? Because when we analyze multiplying n bit numbers, we're talking about counted in terms of how many single bit multiplications you are doing. But here you are not doing, these are not single bit multiplication, multiplying by complex numbers and all that. So if I just go and break it up, work with this large ring of integers and use some fancy stuff, the current best time to multiply two n bit numbers takes n log n log n time, okay. Whatever you can do in the word RAM model in constant time, that's what it means by time. And it is using Fourier transform and integers modulo m and various other things, interesting use of some group theory, field theory is used to get such fast integer multiplications. Okay, so fast Fourier transforms are applicable in a lot of ways in electrical digital signals. You can use it to multiply integers, and you have to be aware of the fact that you are dealing with complex numbers. Okay, so those are sort of the remarks I want to mention, but otherwise it's all about evaluating a polynomial at nth roots of unity and breaking it up into two sub-problems of half the size. Okay, so questions? Okay, so now what I want to do is just give you a couple of more problems on divide and conquer, essentially this recurrence in the domain of computational geometry. Okay, I'll probably do some hand waving. May not do everything, but I just want to give you a flavor of where all this divide and conquer is applied. So let's look at given n points in the plane, find the closest pair. Closest in Euclidean distance. I don't think the distance matters, but anyway, let's say in Euclidean distance. Right, so I have these points like this. So these are some n points given to me. Maybe this is the closest pair. I want to find that pair and the distance as well. Okay. So you can compute the distance in constant time between a pair of points, right? You just square root of x1 minus x2 whole square plus y1 minus y2 whole square. So brute force algorithm will take n square, because you just take every pair of points, find the distance, and then find the min among all that, and that's an n square algorithm. And let's see how we can use divide and conquer to improve it to n log n. So the first thing is we want to divide the points into two halves and find the closest in each of the halves, and then put things together. So how do we want to divide it? Sort the points under what? There are two coordinates. So by the x coordinate, let's say. Okay, so here is the solution, which is so sort the points under x coordinate. So my points are like this. So I sort them under x coordinates and divide it into two halves based on x coordinates, right? So if your goal is to divide it based on x coordinate, all those, half the points are here, half the points are there, do you really need to sort? We studied this last lecture. Find the median. You just find the median of the x coordinates, because maybe sorting is useful, we'll see, but if it may be useful for other reasons, but if the goal is to just split it into two halves where half the points are this side, half the points are that side, then you can just find the median of the x coordinates, right? Median, remember, is faster than sorting. You can do it in linear time. Okay, that's what we saw last time. You can find the median in linear time. So for now, let's say we find the median. Okay, so find the median. So that means we have only spent linear time, because remember, if I am targeting n log n, this is sort of the recurrence I want. So I really don't want to spend n log n time. Sorting would be n log n. So maybe I find the median and divide it into two halves. All those which are, half the points are here, half the points are here. Okay. And recursively find the closest pair here. Right. So maybe this was the closest pair. And find the closest pair here. Let's say this distance is some delta 1, this distance is delta 2. So that's like 2 Tn by 2. Now what do we need to do? Minimum among this, okay, is that all? So minimum among them is one thing. You also need to look at distance between points here and points here, which we have not considered, okay. And among all those points, we need to find the minimum, and let's see if we can do all of that in linear time. Then I have an n log n algorithm, okay. So let's use some more observations, okay. So suppose a min of my delta is min of delta 1 comma delta 2, okay. So I find the closest pair here, and minimum is some delta, and I have this median, okay. So median, the way we define the median, it's one of the points, but let's say I move a little bit so that it is not really, it doesn't have any of the points. Then I have to look at points, distance between points here and points here, but can I throw away some of the points easily by some observations? Yeah, so if something is, so from this point, if somebody is more than delta distance away, delta is minimum of delta 1, delta 2, then I don't need to, because remember I have already found the minimum among the points here. Now I am looking at point here and a point here. If this guy itself is delta away from this point, and then I am going to pick another point, that's even going to be more than delta. So for first observation is that anything which is, okay, somebody said delta by 2. Is delta by 2 enough? Yeah, but maybe there is, if you use delta by 2, there may be a point slightly here and here, you may be missing those points, right? So you just go up to delta. So anything, so I take this median line and look at a strip of length delta. First observation is that anything that fall outside these lines, ignore them, okay. Can I find those points? Yes, because I know the x coordinate of these points, x coordinate of these points, and I just go through my list and see anybody whose x coordinate is beyond that, throw them away. Good, okay. So now I have to find a point here and a point here and find the minimum among them. Okay. Next observation is that, so now let's look at it in y coordinate. Okay. So maybe we sort under y coordinate. Okay. That's going to come to my n log n, but we'll worry about that later. But let's say in these points which survive now, I sort them under y coordinate, and I claim that, anybody see, if in the y coordinate distance, if somebody is greater than delta, again there is no point in comparing those two, right. Even in the x coordinate, they may be very close, right. So there may be somebody is very close, but if in the y they are beyond delta, I don't need to look at it. So the second observation tells me that, so if I have a point here right? I'm considering points in under y coordinate. If I have a point here, then there's no point in comparing it with anybody which is at a distance more than delta here. So that means all I need to worry about is this rectangle strip where this distance is delta and this distance is 2 delta. I don't, so what is my combined part of the algorithm? Consider the remaining points in the y coordinate, and for each point sort them under y coordinates, let's say, okay, it's going to contribute to n log n, we'll worry about it later. Sort them under y coordinates. For each point, I am going to compare it with all other points, right? All other points is too much, that's going to be n square, but I want to argue no point in comparing. If I am doing it in increasing order of y, how many points can really lie on this strip? Because I really need to look at only those points and compare my distance, right? But remember, everybody here has distance greater than or equal to delta, because the minimum distance here is delta 1. Similarly, everybody here has distance greater than or equal to delta. So, if I have a point here, I mean, the really bad case would be maybe somebody here, somebody here, somebody here, somebody here, somebody. Every pair in each one direction, one side. If you take 2 points in this side, their distance is greater than delta because the closest pair in this side is delta 1 distance, and delta is even smaller than or equal to delta 1. So, any pair has distance greater than delta, greater than or equal to delta. Similarly, any pair here has distance greater than or equal to delta. So, the really bad case, maximum number of points, if I look at a point here, then there are only something like 6 points. There may be a point here, point here, point here, because if I have a point here, then I lose my leeway to have another point. So, the third observation is that for every point you really have to look at some constant number, 6 or 8, some number of points, compare with them and find the minimum, because anything above has distance more than delta, no point in considering. So, put them together, at least we have So, I am just looking at points in increasing order of y coordinate. I have sorted these points in increasing order of y coordinates. Okay. So, now I have, let us say, y1, y2, yn, may not be n because not everybody is surviving. Now, I am going to compare y1 because these are all in increasing order of y coordinates. So, I mean, next point will be like here, but they cannot be here because they are too close, the distance is greater than delta. So, if you have a point here, other point may be here, maybe here, okay, maybe here. So, if I y coordinates may be same as well. So, if I look at them in increasing order of y coordinate, I need to look at only some 5 other points to compare with. So, I just take each yi, look at the next 5 points, compare them, pick the minimum, and keep doing it, keep track of the minimum. So, that's going to be, so this part, because I am sorting under y, that's going to contribute to n log n. Okay. Yes, that's a, so let's come back to that, right? So that's a nice observation. So now, so if I really, so is it clear that I have an algorithm whose running time just two. First, I find the median under x and then recursively find the closest pair here and closest pair here, and then the remaining points, so anything which is outside the strip of this delta from the median point, throw them away. That's easy, run through my points and see their x coordinate and figure out whether they survive or not. Out of the remaining points, sort them under y coordinates, and for each point, look at the next 5 points and compare, and that's like an order n. So, the sorting under y is what is taking me n log n. If I do this, this will be like n log square n, okay. doesn't really fit into the master theorem we saw, but you can expand it out and check that this solves to n log square n. So now the observation is to, maybe sort them only once, okay. But important that, okay, so let's again, we should not fall into the trap where we had the recursive step. Also, I need this situation of whatever my input is, right? So let's say pre-sort input under y coordinate. This is my algorithm. So this is done once, right? Now find median under x. And partition all the points into L and R. Recursively find closest pair in L and R. So let's say that's delta 1, the distance is delta 1, delta 2, let delta equal to min delta 1, delta 2, and remove points outside delta strip. Let's exactly see what we need at every step, and then consider remaining points in sorted order of y coordinate. And compare each point with the next 5 elements. And finally, find min among all of those and delta. Okay, so that's the final, you get the points, you get the distance, all that stored. Let's see. So pre-sort input under y coordinate, that's n log n one time, apply your merge sort algorithm. Find median under x coordinate, we know how to do it in linear time, so this is linear time. So this is an outside recursive part. Now I am recursively finding closest pair in L and R. So when I apply recursion, what do I need? I want points in L and R also sorted under y coordinate, right? Because the initial step needed it, so a recursion step also needs it. This is very important to keep in mind. But that's not very hard to generate, right? Why? How do I generate it? So at the recursive step, all I'm saying is I have these L points in L. I want them in sorted order of the y coordinate. I don't want to sort them because that's going to be built into my recursion and contribute to n log n. I don't want to do that because my goal is to do these 2 recursions and then do everything in linear time. But can I use the pre-sorted under y coordinate and get the L and y sorted under y coordinate? Right? I have all the points sorted under y coordinate. They're sitting there. Out of which I want some of them in the L sorted under y coordinate, some of them in the R. It's like the reverse of the merge routine. It's like an unmerge routine, right? I run through the list and whichever is L, I just output them in the linear scan. They are already in increasing order of y anyway. So I get them and put them into L. Similarly, so I got for free, right, in linear time really, that even the points of L sorted under y coordinate. This from the pre-sortedness, I need to extract that out. So, but it is important that you have to build that step into here, because the recursion needs these points sorted under y coordinate, and then removing points outside delta step. That's easy. This is a linear time overall. So this would be this plus a pre-sortedness of an n log n. That's outside the recursive step. So this is an n log n. So overall, it's an n log n output. Okay. So sometimes this is an useful trick that you may not want to do some extra work inside the recursive steps. You may want to do it once and use it. Yeah. 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 Yeah.
So when we are calculating the median, the close 2 points might go out as an outlier.
That's okay. Remember, median point is only on the x coordinate. Median is not on the distances. Okay. Median is just, I look at the x coordinate point, because all I want is in my entire plane, half the points should come in one side and the other half on the other side. So I look at the x coordinates and find the median. So, I mean, if you are worried about the x coordinates being, many of them being same, that's not a problem. Median algorithm works. Median algorithm, which we saw last time, it gives you a linear time algorithm to find the median. The only property is that, okay, there are a lot of elements which are same. What is median? If that's your question, you can put some points here, some points here. Yes, that's not a problem. Just make sure you're the half of here, half of there. So, okay, so I think you have a point that maybe this 6 or 5 I said, there are some anomaly cases where this 5 is not 5 but maybe 8 or something, right? Because maybe there is a point here which you might consider it here as well as here. But in any case, it is some constant number. Maybe if not 5, it will be some 8 or something. Okay. Here's one last problem on divide and conquer. I'm not going to I'll full details. It's again a problem in geometry. You want to find the convex hull okay, what is a convex hull? Any figure. So a figure that encloses all the points. First of all, it has to be convex. Okay, it's a convex hull. It is the smallest convex set that encloses all the points. So if this is my set of points, so my convex hull will look like this. Okay, so this will be like convex hull. This is the smallest convex set that encloses all the points. Okay. So there are a number of algorithms for this problem. So again, let's think of how do I do this by divide and conquer. I will again find the median of the x coordinates, divide it into 2 points. So the median is so useful in that sense, right? The median algorithm we saw, which you can do in linear time, is very useful because whenever you just want to split some points into two equal halves by some measure. So you divide it into two halves. So maybe find the convex hull recursively on each of the halves, and then in linear time you want to put together. Okay. Okay, that requires just getting more into some geometric terms like turns and so on, but you can figure out somehow that what I want to do is that take this convex hull, and somehow I might just do something like this and get rid of these points or something. So I might finally get a hull like this, okay, which will have all the points. So divide it into two halves, find the convex hull recursively, and then there are some clever ways of running through these points, doing some scans, look at the angle by which they are turning, and using all these ideas you can merge, in some sense merge these two in linear time. Okay. So and yeah, convex hull is another well studied problem in geometry. I'm not going to say more about this algorithm. Okay, so with this I think we will stop divide and conquer and move on to something else next time. So I've seen a lot of examples of divide and conquer, including recurrence relations and finding the median of endpoints, which is one of the very clever applications of divide and conquer, not just dividing into two halves or something where you have to carefully pick your size of the partition. Discrete Fourier transform is another nice application. There are problems in geometry where you can use divide and conquer to get a faster algorithm. Okay, so I think we'll stop and move on to something else next time.